Hi, I'm going to talk about a type of attack in cryptography called the birthday attack. It is caused ultimately because the number of possible outputs of a hash function is finite. And the pigeonhole principle says that if there are more inputs into a hash function than there are possible outputs, then there will be at least one output that maps to the same input. In cryptography, this is called a collision. And when hackers find these collisions, they can use them to their advantage in learning how a hash function works. But first, in order to understand what a birthday attack is, we must first understand the concept after which it is named, the birthday problem or birthday paradox. So imagine that there is a room with let's say 23 people in it. We want to know the probability that 2 of these people in the room share a birthday. And for simplicity, let's ignore leap years and assume that every year has exactly 365 days. At first glance, you might think that the probability is super small. After all, there are 365 possible birthdays and only 23 people. But we'll see that it's actually much bigger than you think. So it's easiest to solve this problem by calculating the probability of the people in the room that are not sharing a birthday. And we'll do a simple example first. So for example, what is the probability of 3 people not sharing a birthday? So the first person has 365 out of 365 days. Then the second person has 364 out of 365 days. And the third person has 363 out of 365 days. And if you multiply those together, that is 0.9917, or the probability that all 3 of those people don't share a birthday. Reasonably high probability. But you might see a pattern emerging. This is very similar to a normal combination problem. It is 365 choose 3, and then all of that divided by the sample space, which is 365 cubed. Thus, we can generalize this into a formula. It is 365 choose n over 365 to the power of n, with n being the number of people in the room. And therefore, back to the original problem, it is 365 choose 23, and that calculates to 365 factorial divided by 365 minus 23 factorial, and then all of that divided by the sample space, which is 365 to the 23rd power. And that equals 0.49952. But that is the probability that no one in the room shares a birthday. But we want to know the probability that there is someone in the room that shares a birthday, or 2 people in the room that share a birthday. And we know that there are only 2 possible outcomes. The probability that no one shares a birthday plus the probability that someone shares a birthday must add up to 100%. And therefore, 1 minus 0.49952 equals about 0.5. So it's almost exactly a 50% chance that a room with 23 people in it has at least one shared birthday. But so what? The birthday problem demonstrates that it is deceptively easy for there to exist collisions or overlap even when the number of total options is large. And there are a couple of scenarios to demonstrate why this is bad in cryptography. One is that the more hash collisions bad actors detect, the more likely it is that they can start to learn about the way the hash function works on their way to breaking it entirely. And digital signature verification and security, which is one of the primary uses of hashing, can also be susceptible to birthday attacks. So let's say Bob wants to trick John into signing a fraudulent contract. Bob can create a whole bunch of versions of a fair contract that differ very slightly from each other, and then he can create a hash value for each of those contracts. He also does the same thing for a whole bunch of variations of a similar fraudulent contract, and then creates a hash value for each. Eventually, Bob will be able to find a version of the fair and fraudulent contract that has the same hash value. Bob can then have John sign the fair contract, but Bob can attach John's signature, digital signature, to the fraudulent version that just happens to have the same hash value. And John's signature proves he signed the fraudulent contract because it has the same hash value as the real contract he actually signed. So to avoid a birthday attack, a hash value must be long enough that it becomes computationally infeasible to detect a collision, or at least to decrease the likelihood of a hash collision. This raises security, but then also, in order for a hash value or a hash function to be useful, it has to be not long enough for it to be like too long. Thank you.